Hello again. We are going to do little c, the specific heat capacity of water by the electrical method. An experiment you think was almost impossible at home, but actually is incredibly simple with a bit more cleverness and a little more calculation. And that calculation will stand us in excellent stead for revision. So, what do I need? Well, obviously the most simplest device for heating up water, the one which is most predictable, is our kettle. So the kettle is going to be the basis of the experiment. That's going to give us the heating. That's going to give us the heat supplied. Now, to know how much heat supplied, we have to time it. We have to take the water and put it in the kettle and time how long it takes to boil. If we know the initial temperature of the water and we assume the final temperature is 100, and we discount the fact that some of it may have been turned very slightly into steam, and I mean it will be a very small amount, and we can discount it, as you'll see from the calculation. So, the kettle, what is the power it supplies? Well, of course, it's written on it. On the underneath of the kettle, there is a label. Now, the label reads 2000 to 2400 watts. That means that it will supply 2400. It will take that from the mains, but it will only heat the water up at 2000, a nice round number that's easy for us to use in the calculations. 2000 watts means that every second it takes to heat the water, it will be supplying 2000 joules of heat. So, how are we going to proceed? Well, first, of course, we need to take the initial water. Here I have half a litre to start with. I'm going to make various different quantities of water boil, and then we'll do a calculation and see which is the most accurate, given that we do know what the answer should be, around 4,200. But of course, I need the initial temperature of that water. Now, this is an interesting device you might have in your house. It's a jam thermometer. It is useless for our experiment. The range is too high. It only starts measuring temperature over 80 degrees. The water's around 15. So, looks good, useless. It's the same problem with the clinical thermometer you might have to measure fever. That thermometer, of course, only goes around 30 degrees up to 40 degrees. So again, not much use for water. This is much more useful. I can't put it in the water, but it tells me the temperature of the room. If I leave the water in the room for long enough, it will be the same temperature as the room. So if I know the temperature of the room, then I know the temperature of the water. If you don't have one of these, you'll have a thermostat somewhere in your house. And if you haven't got the heating on, you can assume that the temperature shown on the thermostat will be the same as the temperature of the room. This is the said thermostat. This one's in another room, so I couldn't use it for my experiment. But the parents will know where it is, because this is what they argue about constantly about the central heating. Someone's turning it up, someone else turning it down. So all I do now is I make a note of the temperature, which is 18 degrees. I empty the kettle of all its contents. I put the half a litre of water in it. And as I turn on the kettle, I turn on my stopwatch to know how many seconds it takes to boil. Now we have to watch the kettle. Watch kettle, you know. A watch kettle never boils. One minute and 44 seconds, or 104 seconds if you like. We're going to use that number, and we're going to repeat this experiment for a litre of water, a litre and a half, until basically the kettle's full. Other things you can do to help with the experiment. You can wrap the kettle in a towel. Insulation, lagging. This prevents heat loss. Remember to leave the spout out though, so that it doesn't get dangerous, because otherwise the towel will get very, very hot. But this will help Let me try the experiment again and see if we get a different time. Now, lagging is an important precaution. You always say that lagging reduces the percentage error. The other thing you can do, the other thing you can do to reduce the percentage error is, of course, repeat. Repeat for different quantities of water. So here we go. There we are. This has come down to 126, so it did have some effect. And now for the fun bit. Well, first of all, you take all the readings for time and for the mass of the materials, and then you've got to do the calculations. So here we are doing the calculation. What you need to know is that heat lost is equal to heat gained. Well, the heat lost is lost by the kettle, okay? And the heat gained is gained by the water. And the two of them must be equal to each other. So we have two ways of calculating both things. First of all, we have to look at the formula. Now, the formula for the heat lost by the kettle is to do with power, and the formula for the heat gained by the water is our old friend mc delta theta. So power times time is energy. We've got a half a kilo of mass in half a litre. C, our unknown, specific heat capacity. And the difference was 82 degrees. If you remember, it went from 18 degrees. Now we're going to use the time for when we shielded it in the towel. So it's 2000 watts times the 87 seconds it took the water to boil. And as I said, we had a half a kilo or 500 mils of water. They're the same thing. And 82 degrees temperature difference between 18 degrees and 100. So there we go. Everything goes on the same side. C stays on its own. Bit of simple mathematical manipulation. Get out the old, where is it? Oh, there it is, calculator. Yeah, calculator. Yeah, I found it. Yeah, I didn't know I had it. Would you believe I've been using my phone and I looked in my bag and I remembered I got it. Silly bugger. Anyway, keep pressing the buttons until you get the answer, and that is the answer. It was flashed up on the screen. I didn't make this up. Joules per kilogram per Kelvin, 4,243. That is amazing. That's, yeah. What do you think of it? Well, I agree with you. Yeah. Better than you would get at school. Yeah, I was going to say repeat, but there seems no point when you get such a good result. The actual value is 4,180. So see if you can get closer to that with a towel, with insulation. And if you start with colder water, then the temperature of the water will be either side of the ambient temperature. So any heat gained below room temperature will be balanced by heat lost above room temperature. This is a standard method or precaution. Good luck. Send me the results. Happy holiday.